All right, so I'm going to talk you through the group test like I might answer questions if we were in class. Question number 1, find the equation of the tangent line. So as you all know, we need slope for a tangent line, so we have to take the derivative of this equation. Derivative of x is 1. Derivative of natural log is 1 over, in this case, the y squared minus 99. And then we've got that chain rule piece. So you multiply by the derivative of what's inside, which gives you that 2y. And then the chain rule of y is multiplying by that dy dx. Now in this case, we don't need dy dx solved for all alone. So at that point, I substituted in the x and y values. So 0 for x, which we didn't have any x's, and then 10 for y. And then I numerically solved for dy dx to get the 1 over 20 for our slope. And then I just used point slope form. You'll see that off to the left in that box, y equals that 1 over 20 times the quantity x minus 0 plus 10. But of course, x minus 0 is just x, so my final answer did end up being in slope-intercept form. Although for the most part, you can just leave your answers in point slope form. Question 2, just find the derivative. This time we do have to solve for it in terms of x and y. So derivative of x cubed gives us that 3x squared. Derivative of natural log, again, that reciprocal, 1 over y to the 5th, times the derivative of what's inside, that 5y to the 4th, and then derivative of y, dy dx. On the other side, that derivative of 4 gives us 0. So I subtracted the 3x squared from both sides, and then I multiplied by the reciprocal of 5 over y, so times y divided by 5, so that's how the y ended up in the numerator in the final answer and the 5 in the denominator. Question 3, find the general solution. So we're looking for the integral. Since we're given the derivative, dy dx, we want to integrate to find the original function. So first of all, separate those variables, multiply both sides by dy dx, and then I used u substitution on this one. I noticed that the derivative of cosine is sine, pretty much, which is in the numerator. So I let u equal that entire denominator. I just had to take care of that negative sign, so that's why we've got that negative sign out front after I integrated the y. We've got that equals negative integral of 1 over u du. And the integral of 1 over u gives us natural log. So we've got the negative natural log of u, and then for my final answer, I subbed back in that 1 plus cosine of x. Now in this case, because the range of cosine of x is negative 1 to 1, once you add 1, that gives it a range of 0 to 2, which other than 0 are all positive values, so you could drop those absolute values in your final answer, but I would accept it both ways. Question 4, very similar, find the general solution, and what I see is that 3 to the x to the 6th has the derivative in that function with that x to the 5th being multiplied out front. So I used u substitution again. Derivative of x to the 6th gives me 6x to the 5th. So I take care of that extra coefficient by dividing both sides by 6. And then when I sub that back in, I just pull that 1/6 out as a coefficient. And then we've just got the integral of 3 to the u du. The integral of that, because it's not base e, we've got that extra 1 over natural log of 3. But then the integral of an exponential is itself, so times that 3 to the u with that extra 1/6. And then subbing back in for u becomes 3 to the x to the 6th again. All right, example 5, we're looking for a particular solution instead of a general solution. So we're given a point so that we can solve for c. Start by integrating, separating those variables again. This time, let u equal x to the negative 1, which is that exponent for e. You could rewrite that with a negative power instead, because when you take the derivative, you get that negative x to the negative 2 dx, which is the same thing as that 1 over x squared. We've got that x squared in the denominator for our original integral. Pull that negative out front. Our exponent, 1 over x, becomes u. And then, like I said, that whole denominator dx becomes du, so we can integrate that. The integral of e to the u is e to the u plus c. So then we go over here, substitute back for x, that negative 1 over x, and then replacing x and y with those values from our point. So x becomes 1, y becomes 2e. We end up with negative 1 over e, this negative exponent moves it to the denominator. Adding that to both sides, that becomes our c. So this gives us our final equation. Example 6. Equation of a tangent line. So of course we need our slopes. So we're going to take the derivative. The derivative of arcsine is 1 over the square root of 1 minus whatever you're taking the arcsine of squared times chain rule, derivative of what's inside. So that 8 moves to the numerator. 8 squared becomes 64. And then I can replace that x. Again, we've got a point. So we're going to substitute that x value into our derivative right away to solve for the slope. 8 squared again gives us 64. Square root of 2 squared gives us 2. So our 64's cancel, leaving us with 1 minus 1/2, which is 1/2. Square root of 1 is 1 over the square root of 2. And then when we multiply by the reciprocal, we actually get 8 root 2 for our slope. So think about this as 8 times root 2 over 1. And so that 1 in the denominator doesn't help us at all, doesn't matter, simplifies out. Over here, I'm just showing how I rationalized the denominator. We actually really didn't want to use this value for x because it would have made the math without a calculator much more challenging for solving for that slope. Putting this in point slope form, if you did choose to leave it unrationalized, that's fine. I would accept that. But then the second option is with that x value rationalized. Number 7, just finding the derivative. We've got implicit differentiation. So we have the derivative of 3 times e to the xy. The derivative of e is itself, but then the derivative of that power is product rule. So the derivative of x times y is 1 d2 add 2 d1. That's what we get inside the parentheses here. And then the derivative of that negative 2y squared gives us a negative 4y chain rule dy dx. Derivative of 5 is 0. So we need to simplify. I distributed my 3e to the xy to both pieces inside the parentheses here. That's what I got here and here. And then leaving that last term, that negative 4y dy dx alone. And then I did two things at once. So we have two terms with the dy dx. So I factored the dy dx out of those two terms. And then the plus 3y e to the xy I subtracted to the other side. And then the last thing I just divided by the parentheses, what I was multiplying by the dy dx to get my final answer. Number 8, we have to recognize one of those arc trig patterns here. First thing I notice is there's an x on the outside, so this is making me think arcsecant, and it's the only one with the x outside the radical. It is the square root of that x that's inside, so my u is just regular plain old x, and then my a is the square root of 9, which is 3. So the integral of that would be 1 over 3, or 1 over a, times the arcsecant of the absolute value of x over a, which again was 3. This one's a definite integral, so we don't need that plus c. We're just evaluating from 3 to 6. Subbing 6 in for x over 3 gives me 2. Subbing 3 in for x gives me 1. And then I use arc cosine to help me evaluate those arcsecant functions. So I flip both of them, arc cosine of 1/2, and then arc cosine, of course, the reciprocal of 1 is still 1. And then that gives me those unit circle values of pi over 3 and 0, which gives me a final answer of pi over 9. Number 9, differentiating. So this one's got some chain rule going on. We're going to keep that 9. That's just a coefficient that goes along. The derivative of sine is cosine. So then you leave what's inside alone. That arc cosine stays the same, times the derivative of what was inside. So that's the derivative of the arc cosine. Negative 1 over root 1 minus t squared. That's that pattern for the derivative of arc cosine. Cosine and arc cosine are inverse functions, so they cancel each other out. So that would leave us with just the t, which I'm going to multiply by the 9. And then eventually I'll multiply that by the negative 1 to get that negative 9t in the numerator. And then my denominator just stays that root 1 minus t squared. 10, 11, 12, these are all review questions from pre-calc. So we have to think about the range of the arcsine function. Arcsine is half moon because it's positive in the first quadrant, negative in the fourth quadrant. So we have to think about rotating backwards into the fourth quadrant. That gives us that negative pi over 6 value. All right, number 11. So this is where we have to set up a right triangle. And I realized as I did this one that maybe not all of you have this Pythagorean triple memorized with 9, 40, and 41. I promise you the one on the no calculator test will either be doable by hand or it'll be a Pythagorean triple that you're pretty familiar with. So apologize for that on the group test. But basically I set this up with, here's our theta. So sine would be opposite over hypotenuse, solving for the missing side, and then looking for cosine of that angle because the angle would be the output of the arcsine function. So cosine of theta would be adjacent over hypotenuse, or 40 over 41. And finally, number 12, thinking of those log rules. 6 to what power gives you 1 over 36. Some of you might be able to think about that with no work, but I wasn't initially thinking I'd create a video for those, so I wanted to make sure I was really clear with my work. Turning that 36 into a 6 squared, and then using our power rules, making it a 6 to the negative 2. Therefore, 6 to the negative 2 power gives us 1 over 36.